Hello, everyone. My name is Xiang Wei. So today I will be going through the summer 2022 midterm with you. So yeah, let's get started. So for the first question, an environment is deterministic if the next state is completely determined by current state and the action. Yes, it's true. So like this is just you can think about the definition of a deterministic state. So you have a current state and you take some action and it's determined to be the next state instead of by chance. And the second one is, so a reflex agent selects actions based only on current perception and ignores the rest of the perception history. Yes, it's also correct. So what it does is a reflex agent will only consider the heuristic and choose the next action by the heuristic. So yeah, it's also true. Oh, it's pretty big. So the third one, depth first tree search is optimal for finite state spaces. So for this one, it's actually false. And first, to specify the optimal, we mean the cost optimal. Someone asks whether it's cost optimal or space optimal. So we want to make cost optimal. And so it's not optimal. The reason is that, okay. And the reason is if you have a depth first search, it will always go to the leftmost branch and to go all the way down and go to the next. So it will go through this and it will not consider cost. So it's false. And 4, there exists a problem with a finite solution and a constant heuristic, and the number is strictly positive. So this is also false because we know for a heuristic to be admissible, it should be less than the true cost, less than or equal to the true cost to the goal state. So, but for the goal state, the heuristic for it should be determined to be 0. But here, the heuristic is C, which is larger than 0. That's why we shouldn't choose it. Yeah, so the fifth one, in UC uniform cost tree search, if a goal state is added to the frontier, it must be the goal state that optimal solution reaches. So one thing for here, you want to make sure is the cost should not be negative, because if the cost can be negative, then we need to look at more states and to determine. But here it doesn't make specify it's negative. It cannot be negative. And also, when a goal state is added to the frontier, it's only added to it. It may explore other nodes first and go back to this frontier. So it's a different path. That's why it's not when it's added to the frontier, but when it's get out from the frontier. So it's false. So the fifth one, it says for the CSP, the asymptotic runtime of naive backtracking search is guaranteed to be better than that of the DFS. So this one is also false. The reason is for like, what's the difference between a backtracking search and a DFS? So it's composed of three things. The first one is DFS. It uses DFS's method. Second one is no conflict. And third one is in order, like order. So what the second says is just when you assign values to a new variable, you should make sure that value is not in conflict with the previously assigned values. And also for order is you should assign variables in order. And nothing says like the speed of backtracking search will be absolutely better than DFS. Instead, all of them, like both of them, will search for the go from the leftmost branch to gradually to the rightmost branch. So it's false. And the seventh one, so the worst time of AC3, like arc consistency algorithm, is O e to the power of 2, d to the power of 3, where e is the number of arcs. So this is wrong. This arcs should be nodes, should be n squared d3. So it's also false. And the eighth one, the LCV heuristic, stands for least constraining variable. Actually, it shouldn't be variable. Instead, it should be value. And the ninth one, so it should be false. The ninth one, backtracking search is a method of informed search. So we can see from question here, question 6, it just ran as just like the DFS to go from the leftmost branch to the rightmost branch. And so it doesn't have anything like heuristic to inform you. That's why it's uninformed search. So this one is also false. The 10th one, using the same fixed variable and value ordering. This will backtracking search with forward checking and AC3 will always return the same solution to CSP. So yeah, the reason is also for this question, it is actually true. Why it's true? So we need, one thing is really important is the forward checking and AC3. They're just method for us to decide which possible value is impossible. So it just helps us to like fail earlier and to speed up our search. It doesn't change anything about the core, which is backtracking search. So using both of them to speed up our search won't change the actual solution of it. That's why this is true. So the 11th one, when combine MRV and LCV heuristic together, they're just the method for us to, MRV is to fail earlier and LCV is to find the most possibly successful node for a value first. And so it says we can always improve the asymptotic runtime with naive backtracking search. So naive here like doesn't mean anything. It's just normal vanilla backtracking search and with random ordering. So this one, the answer is false. So we can say using this ordering, we may have speed up we may speed up our search, but like different cases we can have different cases, like just when you assign values, maybe the value that is most constrained will like it is actually the only successful assignment. So yeah, maybe just for the example, just leave you as an exercise, you can think about it. So yeah, they're just they may improve the speed, but they're not guaranteed to do so. And so the 12th one, if random variable like A and B are independent, then we have PAB equals to PA times probability of B. So yeah, it's true. And we can just write it as PAB is equal to PA given B times PB. And if AB are independent, then PA given B will be PA. So this will be PA times PB. For question B, select all the algorithms which are complete. And so for DFS, it is false, because for DFS, it will go to the deepest node. However, if there's a loop, then it will never reach the deepest. It will just go around this loop and never stop. So it's not complete. And BFS, yeah, it's true. So for what BFS do is it will just from a tree, it will just go here and here, just depth by depth. And so this is actually complete. And greedy graph search with consistent heuristics. So here it is actually false. What is a greedy search? So for a greedy search, it would just look at the so why it is false is that for the greedy graph search, it only looks at the if the circumstance is optimistic, if it's good, then if it's all the search space, then this is the goal state. Like the search algorithm would just go through this, and the heuristic will just inform it to find the goal state very quickly. However, there are also another case when it's not lucky. Then if the goal is here, maybe the search algorithm will just find all these states and this state and all of them, and will not explore the go state. Why? It's instead of its infinite loop, the reason is it may be trapped. Like if it just come to here, and for other heuristics it's already explored, then it will not explore because it's graph search, and so it will get trapped here and will not be able to come here. Yeah, so it's not possible. And for A star tree search with a bad heuristic, so for this one, we know that A star tree search is just UCS plus heuristics. So UCS is guaranteed to find a best solution since it just rely on cost. So no matter how bad the heuristic is, it is guaranteed to find the goal. So we should choose B and D. And for the second one, so if a heuristic is consistent for A and B is a relaxed problem of A, then H is also guaranteed to be consistent for B. Actually, this should be go inverse. So if H is consistent for B and B is a relaxed version of A, then H is guaranteed to be consistent for A. Why is this the case? So it's false, but is it will admissibility guaranteed? The answer is also no. So why not? If like, what is a relaxed problem? A relaxed problem is maybe you have other limitations or rules, but a relaxed problem is just suppose you don't have those rules, which will give you a shorter, a smaller cost sometimes. For example, if you in a Pac-Man game, maybe there are walls and ghosts. So a relaxed problem, like, so this is the original problem. There are walls here. And if a Pac-Man here want to get the food here, then the best way for it to go is just to go this way. But a relaxed problem for this one will just be suppose there's no walls. And okay. And then this is Pac-Man, and this is the goal. And so it will just directly go from here to here. So we see from this counterexample, if F is consistent for like, maybe like we already talk about consistent, and then we'll talk about the admissibility. So if H is admissible for A, then H can be 1, 2, 3, 4, 5 steps to get there. And then B, like this is A, this is B, and this is the relaxed version of A. Then is it guaranteed to be admissible? Like if we have a heuristic 5, and then 5 is greater than 1, 2, 3, than the actual cost. So this will not be, it is just to say H is greater than cost. So it's not admissible. And so that's why we choose D. If it's not admissible, then it's definitely not consistent. Then for question 3, let me just quickly clean it. So for heuristic, if we have like hx1 larger than everything along the path, and hx0 is 0, then it is consistent. I think the direction for it is also wrong. What we can say is definitely correct is if H is consistent, then the cost along the path will be strictly non-decreasing, non-increasing. But if it's decreasing, it's not definitely going to be consistent. For example, just yeah, hx1 can just be 1000 when the actual cost is 5 or 6. And like hx2, maybe it will be 3, and the goal will be 0. Then for hx1, it will be like way larger than the actual cost. So it's false. And so then it's false, it's easy to determine, but if h is admissible, can we conclude that h is consistent? The answer is also no. Why the answer is no is also like the true cost, maybe the true cost is 5 and then 3 in that case. And if h is admissible, then the first cost can just be 5, then it's admissible. And the second cost, it should be less. Maybe we can just give it 1 because it's less than the first one. So it's also satisfy the question. However, 5 minus 1 is larger than 5 minus 3, which means the difference in heuristic is large than the actual arc cost. And so we can still not conclude that h is consistent. So this should also be false. And for the last question, the first question is, if two players, they play rock, paper, scissors, and how can we model this problem? So the first says it's a single player search problem, but we have 2 players, so that's a definite wrong. For a second one, this problem can be modeled as an expect max search. But for an expect max search, what we have for sure is we know the probability for choosing both actions, like for choosing a rock, paper, or scissors, but we just choose it indeterministically. So we cannot calculate the expectation of the actions. That's why we also didn't choose this. So what we are left with is the minimax search. Why it can be modeled as a minimax search? First, like they just want to do it they just want to do it to win. And so this game is a zero-sum game. And then like 2 players, they just we can just model them as one as the maximizer and to increase his score, and one as the minimizer, which is to decrease that player's score, which means to increase its own score. So yeah, so we should choose this.